In this entire lecture series, we are going to look at what happens to an aircraft or a spacecraft that is about to leave the surface of Earth, go to higher orbits, higher altitude, and do some maneuvers that we have expected to do it for. To start this entire series, we have to first go through some of the basic concepts of gravitation, gravitational pull, what is escape velocity, and then understand how these aircrafts behave, or the spacecrafts that we have designed behave from lifting off from the ground and going into the orbit. So imagine this is the surface of Earth and you have an aircraft which takes off from here and goes to a higher orbit. This spacecraft, from its motion at time t equal to 0 till it settles down in this orbit, is something that spaceflight mechanics is very much interested in. But this entire maneuver is a function of three things: the mass, the propulsion system that drives it, and the gravity. Now this g, the gravitational constant, we have always been assuming this constant for our all calculations so far, is a very notorious thing. The origin of this g is in Newton's fundamental laws of gravitation, in which he said if there is mass m1 and mass m2 separated by distance r with the radius vector of r bar, then the gravitational law dictates that the force, remember this is a vector, so the force that is applied by m1 on m2 is simply g into product of mass by the modulus square. This means it is a linear scalar distance and a pointing vector in the direction. Now this can be Earth and this can be an object, or these can be two equal sides. This can be Sun and this can be Earth. But the law holds across distance in the universe. This Newton's law is a fundamental foundation of the entire maneuver. When you are trying to understand what happens between the interaction pull, we have to first find out what this constant is for Earth. So imagine that you have got a mass which is on this surface, right? It's a happy man sitting on the surface of Earth. The gravitational pull is simply gm upon r square, because this is g multiplied by m, which is the mass of the person, will give you the force F equal to mg, which we have always been studying in the textbook. This is the constant for a particular planet. For our Earth, your m is defined, r is defined, g is a global universal constant. So this gives you the value of g. But if you analyze this closely, it is function of this mass, which means we have to first understand, are we looking at entire Earth's mass, or if I am inside, say I have done a deep tunnel, say 1000 meters, how much mass am I really interacting with? So that's the first value. Second, the radius, which means from the center of Earth, am I at the surface or am I at some height? This foundation will first help us understand writing the equations of force on any object doing some trajectories around the Earth or any other planet. Now let us look at one particular problem in which a mass is inside the surface of the Earth, which means it is inside the body. Imagine that this is the entire Earth with radius of r, and your object is beneath at the depth of d. The mass of object is m, and Earth's mass is of course capital M. We are interested in now actually trying to find out what is the relationship for this particular depth to the force that this mass will experience. Again, going fundamentally, this is the total mass of Earth which is going to be interacting with this particular object mass, and this other mass, gravitational pull, is not relevant, simply because it's symmetric across, right? So the force is, so if I have say this small dm mass of Earth here, and this is the mass, the vector of the force that will get produced will get cancelled by equal and opposite mass here, which means because of the symmetry of the shell from outside, I'm not really bothered about what it does to this particular object in terms of force. Now if I have to simplify this, I will write the force as g m dash. This m dash is the effective mass of the shell that actually interacts with this capital mass, upon r minus d whole square. Right? That's the magnitude of the force. It's a still vector, I'm just looking at the magnitude. Now m dash is simply rho into 4 by 3 pi into r minus d cube. Right? Because it is simply the mass of this shell. Rho is assumed to be constant across the earth, that is reasonable assumption for small depth and can actually be always be used. Only the problem will be if depth becomes very much similar to radius of earth, this assumption falls apart. Having done this, let's substitute to get g upon r by v minus whole square rho 4 by 3 pi r minus d cube. So this is a force. We also know from our relation that the force equal to mg that it experiences had it been on the surface is simply g mm upon r square, right? And the mass here is rho 4 by 3 pi r cube m square. I have simply substituted so that I am able to substitute this density rho using the known constant g on earth, which means rho from this equation is simply 3g upon 4 pi g, correct? And r constant. This is what I have to substitute in this formula to get g upon r minus d square 3g upon 4 pi gr into 4 pi by 3. I can immediately cancel these out because they are not required. R minus d whole cube. So r minus d still remains here. And what you get is simply 4 pi by 3 is gone. So g r minus d upon r. So if I have to effectively write it here, force experience is simply r minus d upon r into g, which means 1 minus d by r of g. So to plot a graph of variation of this force with respect to depth is when depth is equal to 0, it is maximum g, right? That is the surface. And at r equal to d, it becomes 0. So it's a straight line having the slope of d by r. That's the understanding of what happens to an object which goes beneath the surface of earth and how much force it experiences because of the gravitational mass. This is the first pivot. Second pivot now is to understand what happens to an object at height h. This will help us to do our maneuver calculations, and then using combination of these two, we will look at an object which is at an equatorial altitude of theta, because your earth is actually made up of these equators, right? So if I have to see the earth as a picture, I will actually have this earth which has these equators and these latitudes. Right? All the latitudes and longitudes are basically from these fundamentals of theta and psi. So any object, say having a longitude at an angle theta, I will try to find out its gravitational pull, and these three will form a foundation of how the trajectory of object goes from the surface of earth to the space.